Right. So today I'll be discussing a bending moment type problem, right? So let's see how to sketch the bending moment, right? So now first I will sketch the problem, right? So we have uniformly distributed load, right? Right, we have a uniformly distributed load, right? This is A, this is B, and so this is a roller support, right? What sort of support? So this is a roller support, right? And so this position is B, right? This position is C, right? And we have position D. Later I will tell you the distances, right? So this is position D, right? Applied moment is there at D, that is 60 kilonewton meter. Then we have a point load 20 kilonewton. Point load of 20 kilonewton at point E. Okay. Then we have a uniformly varying load, right? So this is how I am going to sketch that, right? Right. So this is what uniformly varying load. So now the position is FH, right? And at this position H, again there is a roller support, and at position G there is another point load, position G, right? Point load of 40 kilonewtons, right? So now I will again check that. Now here the uniformly distributed load is, the value is 30 kilonewtons per a meter, right? 30 kilonewtons per meter, right? 60 kilonewton meter, then 20 kilonewton point load, then the next thing is, what is the value of that uniformly distributed, so uniformly varying load, what is that? It is 100. So that means this length, like this line, the larger one, this is 100 kilonewtons, this is 0, right? So it is varying like that, such that this is 0 kilonewtons and this is 100, right? Okay. Now okay. And the next thing is the distances. A to B distance is 1 meter. B to C also again 1 meter. 1 meter, 1 meter. 1 meter, 1 meter. Then again from C to D distance is 1 meter. D to E also distance 1 meter, right? E to F also the distance is 1 meter. And F to G also the distance is 1 meter. But G to H, I told you this is H. G to H, the distance is 2 meters. Okay, right. So now what is the very first thing that we have to do? The first thing is that we have to find the reactions, right? Here we know there is a roller support, right? So we have a reaction along the upward direction, right? The reaction that is exerted on the beam, right? We have a reaction that is exerted on the beam by these supports, right? So we have a reaction acting on upward direction, right? So let's say this is RB, reaction B, right? And here also we have a reaction RH, right, acting along the upward direction, right? Okay. So now we can write an equation, right? So now we can write an equation for the vertical equilibrium, right? So let's write an equation for the vertical equilibrium. Write an equation for the vertical equilibrium, right? Vertical equilibrium. Now every time I am telling you this thing, right? Every time please write the information, right? Then it is easy for you to understand. So now how can we write this? So we will say upward forces. Now the system must get balanced, right? So we can say upward forces must equal to downward forces, right? That act on the beam. So what are the upward forces? We have RB, okay. We have this reaction RB. Then we have this reaction RH, okay. RH. Anything else? This is taken. Then we have this applied point load over here. What is that? 40 kN. Upward and upward. Is that all? Yes, that is it. Right? Yes, that is it. And then equals the downward force. What are the downward forces that we have? Oh, we have this uniformly distributed load, 30 kilonewton per meter load for a distance of this much. That is acting on the downward direction. So 30 kilonewtons per meter for a what sort of a distance? 2 meter distance. So 30 multiplied by 2. Then see, this is also acting downward. See this point load 20 kilonewton, then plus 20. Then the next one is this one, this uniformly varying load. So how to find the total load that is affected over there? That is the area of this triangle, right? What is the area of the triangle? This part, half into base. What is the base? This is 2. What? The base is 3 meters. Into height. What is the height? 100. So then we have this equation RB plus RH plus 40 equals 30 into 2, 60 plus 20, 150. So 150, 156 to 210, then 230. So 230 minus 40 will be 190 kilonewtons, right? RB plus RH equals 190 kilonewtons, and this is one equation, right? So that we have obtained by considering the what? Vertical equilibrium, right? Now the next thing, right? What is the next thing now? So now let's write an equation by considering the moments, right? So now I will erase that, right? Right. So you can pause the video and write. Okay. So now I will write the next equation considering moment at the point H, right? Considering the moment, right, at this point, at the point H, right? So now let's tell me, right, what is the advantage if you consider moments at this point, right? Then you do not have to worry about this reaction, right? If you are going to consider moment about this point, then you don't have to worry about this reaction, right? So now let's take moment due to all the forces that is affected at this point H. So we will denote it by MH. So we'll take along what direction we should take. We'll take around that clockwise direction. Right? So like that, this direction, clockwise direction. Clock. So what is the first force? First force, see, we can consider RB. See, this is going in the, see, the moment on this point will be clockwise because of this reaction RB. RB times, so what is this distance from here to there? So those are the things that you have to be very careful. 2, 1, 3, 4, 5, 6 and 7. So it must be RB into 7. Let me check, because every time I'm checking with the marking scheme, right? RB into 7, right? Right. So this the momentum that then what about this one? Now here there's a special scenario, right? Here first of all you have to find the total distribution. 30 kilonewtons per meter into the distance is what? 60. No, distance is 2 meters. So 30 into 2, that is the total load. So now what is the particular point that 60 kilonewtons are acting? The center point, the center of gravity. Center of gravity is over here, right? If this is 2 meters, what is the center position? Center position is here, right? But that is acting in the downward direction through the center of gravity. So then minus, what is the total distribution? 30 into 2, that is one part, okay? So what is the distance? Acting here, so that means 7, right? So now you got it, right? Now look at this special guy. There is this is an already applied moment. So don't worry about that. Not a force, applied moment, right? It's applied moment, and here you do not have to worry about the perpendicular distance, right? You do not have to worry about the perpendicular distance. Applied moment. So just write 60. Why positive 60? Because positive signal, see the direction clockwise. That is also okay. Then what is the next thing? Next guy is this point load 20 kilonewton. Going what direction? Anti-clockwise. So we are putting negative. Okay. Right. Now, okay. Right. 20 kilonewton, so anti-clockwise, right? So 20 multiplied by, what is the perpendicular distance? 134. Perpendicular distance must be 4. 20 into 4. Then again look at this one. Here we have a point load. What is the value? 40 kilonewton. 40 kilonewton. What will be the direction? See, clockwise direction. So positive 40 into the distance 2. 40 into 2. Is that correct? Yes. 40 into 2. The next guy is this, uniformly varying load. Uniformly varying load. Be very careful. Uniformly varying load. So anyhow, the resultant. Now, what is the position where the resultant force is acting? Now see, this is a triangle. Right. The resultant will act at a point that is 2/3 from this vertex, right? Center of gravity of a triangle, you know that, right? It will act at a position that is measured as 2/3 of this length, right? So that means 2/3, 2/3 of this length means somewhere here, right? Right, so I will sketch again if you want. 2/3, the center of gravity due to this uniformly varying load is actually at a position 2/3 from this vertex, right? So then what is the perpendicular distance? Perpendicular distance will be 1/3, right? Because here actually the length is 3 meters, so the distance is 1/3. So the moment is actually negative. So negative, first the total intensity half into base 3 into height 100 into perpendicular distance is 1/3. Is it correct? Yeah, actually wait, not 1/3. Wait, not 1/3, because here the total length is 3 meters. So 2/3 of 3, right? 2/3 of 3 is 2, right? 1/3 of 3 is 1, right? Okay, be very careful. What I told, the center of gravity, right? That means the entire weight is acting at a point that is measured as 2/3 of this total length, right? 2/3 of the total length, this one, right? That is somewhere here. Actually the length of this base is 3 meters, right? So 2/3 means what? From here to here it is 2 meters, right? So then what is this distance? it is not 1/3, it is 1, right? Because why? Again I am telling why, because it is actually 1/3 out of 3. So here it is not 1/3, it is what? 1. Very careful, na? Yeah. So now let's simplify. So now if you are going to consider moment about this point H, right? When considering the equilibrium, the resultant moment mh must equal to 0, right? Okay, moment must equal to 0, right? So no problem. So now 0 equals 7 times RB, right? Then minus 30 into 2 into 7, then 60, 420, positive 60, minus 80, again positive 80, then minus half into this means half, 50, minus 150. So then 0 equals 7 times RB. We'll keep minus separately, and minus, see this guy, yeah? Now this is all about simplifications, right? 7 RB minus 420, minus 420, minus 80, minus 500, right? This one minus 650. Then what are the positives? 140, this and this. So then 0 equals, let's do the simplifications, minus 650, positive 140. That means 550, 550, 510, minus 510. So then 7 RB equals 510. So then what is RB? RB will be 510 divided by 7. Right? So what is RB? RB will be 500. Carefully check the simplifications. RB will be 510 divided by 7. So if you find that answer, it will be 72.857, huh? 72.857. So let's consider it as 73. 72.857. So let's consider it as 73 kilonewtons. Right? So now be very careful. So now we have calculated that the reaction RB, right, over here is 73 kilonewtons, right? And we already know from the equation for the vertical equilibrium, we know that RB plus RH equals 190, right? So then if you subject RH, right, then you can find what is RH, because RH equals 190 minus RB, right? RB we have calculated. So now what is the value of RH? That is 117 kilonewton, right? Okay. And here be very careful, right? Here now I have already told you about this, this triangular load, right? Triangular load, that means we call it UVL, right? We call it what? UVL, uniformly varying load, right? And I told you that this length is 100, right? But be very careful, the unit is actually, because actually this line represents a kind of an intensity, right? Load intensity, but this length is actually 100, see, 100 kilonewtons per meter, right? So if you want to find the total effective load, you have to find the area, half into base into height, right? Okay, right. So now the next thing is to do the sectioning, right? So now we have to sketch shear force and bending moment diagram, right? So this is it has like so many complicated steps, right? Okay, so doesn't matter, right? So now the first thing is to do the sectioning, right? So we do something called sectioning, right? We do something called sectioning based upon the points where we have different types of loads and different types of, not only loads, even different types of moments, right? So we do sectioning based upon where we have like different types of different types of experiences, right? So now just consider the first section, right? Okay, so now we will consider the first section, right? Let me teach you. Now I will do this for some 3 to 4 sections I will do, right? So then you can understand how to do the future steps, right? So first section is that you know that here we have a reaction RB. You know that, right? We have a reaction called RB. What is that? RB is 73, 73 kilonewton. So at this point, now what is this length? This length is actually 1 meter, right? But you know that when it at here, right, at this point we have a different load. So that is the first experience that it meets, right? So that is how we do section, right? So now that means, now wait, I will again sketch this, right? Then only you will understand it, right? I will again sketch this guy, okay? It takes time, but doesn't matter. First, right? What's the number one thing? I have to do the sectioning, right? So now here we have the reaction RB, but I will sketch it like that. RB, okay? So RB equals 73 kilonewtons, okay? So this is A, this is B, this is C. This is at the point D, 60 kilonewton meter, and then here A, B, C, D, E, we have 20 kilonewtons, okay? And this triangular load, right? Uniformly bearing load. Not only that, even at here we have 40 kilonewtons, and here we have RH because of what? The reaction due to the roller support. What is that? 117 kilonewtons. Right? Now wait. Now let me teach you how to do that. Right? Carefully listen. First section, we define a section called AB. Considering section AB, right? Now how we define this section AB? 0 greater x lesser. Now what is the total length up to here? 1 meter. Right? So this is how we do that. Right? And here we say not only greater, x is greater or equal to 0 and lesser or equal to 1. Right? Okay. Now let me teach you that. Let me teach you about the sectioning. Now sectioning we do based upon the different types of loading and moment conditions that you meet. So the very first moment, the very first visitor or the like new experience that you meet is up to here, right? Up to the section AB. So we consider one section as AB, but the scenario is we are going to like cut or we are going to break the section little bit before the ending point. Little distance or gap before the end. Okay, so we are going to break it from here. Agree? So we are going to break it from here. So now what is that distance? X. When I do it for some several steps, then you will understand how to do that, right? So this is how we do it. First section, right? Then shall I teach you about the second section? Let me teach you about the second section, right? Second section is, now see this at this point C is the end of this uniformly distributed load. What? This C is where we see the end of this uniformly distributed load. So the next section is, now when you are going to consider the next section, be very careful, that is completely a new experience, right? So we are not going to consider this part, right? Shall I do it now or later? No, first we'll finish for this section, then I will go to the other section right now. Now the most important part, right? Now we are going to consider for shear force. What? Shear force. Right? So now we are going to write shear force equations for the section AB, right? Now in shear force there is a very important part. So now just consider this, how to say that, so let's consider this beam, right? Now when considering shear force there is a direction. If now this is what, if you observe from the front, if you observe from front, what is this side? Left side. But to me it is right side, huh? Okay, to me it is right, not to me. If you observe from your side, what is this side? Left side, right? So if any force that causes your left side to go up is what we call as positive shear. Any force that causes left side to go up, positive shear, right? So now just consider, so now we are going to consider only this section where we stop the section, right, or where we cut the beam little bit before the end P. So what are the forces? Now forces, do we have this reaction RB? No. Why? Because we are going to stop the section little bit before that, so we don't have this reaction. Careful, huh? What is the only thing we have? The only thing we have is this distribution, right? 30 kilonewtons per meter distribution. So the resultant of this distribution acts downwards, right? So downward means this will never allow the left side to move upward, so it is negative shear. So minus 30 into, what is the length? Length is x, right? 30 into x, because now x is the length of the section. See, starting from here to here, this is where we cut the section, right? So minus 30 into x. So now this is the general equation. Now this is the general equation for the shear force for section AB, right? Now there is a very funny part. When x equals 0, shear force is 0 kilonewtons. When x equals, now let's think that we are going to say x equals 1 to the extreme super length. When x equals 1, then shear force is what? Minus 30 kilonewton, right? Just note this down, right? Okay. Oh, now I will erase this part. Okay. So now we have to write for the bending moment. I hope this part is clear, right? The sectioning scenario you will understand when I do it for some 3 or 4 sections, right? As we do not have space, I will erase this part. Okay. Now again, considering for the same section 0 greater equal x lesser 1, now I am going to consider for bending moment. What? Bending moment. Now this shear for this equation I will erase. This whole part I will erase, right? Now again, for the moment also the same scenario. Any moment that causes the left side, that is viewed from your side, any force that causes left side to go upwards, right? Any force that creates, or any torque or any moment that creates the left side to move upwards, that is positive bending moment, right? So bending moment equation for the same section Bm. Now how to write that? What is the force? Now see, this is our section. Shall I sketch the section again? See, this is our section. What is the length? X. See, this is our section. What is the resultant, or what is the total load for the section? Total load will be, the length is x, so total load will be 30x. So where it is acting? So it acts at the center of gravity. Center of gravity is at the mid. So where is the center of gravity? Center distance will be, if I am going to start from this end, it will be x divided by 2, right? Okay, because it is distributed for a length of x, so total load will be 30 into x, so 30x. So that entire load will act at the center of gravity. which is at a distance of x divided by 2, right? It is very symmetric, right? So now, now the thing is, you are going to get bending moment, right? This is the most important part, right? So I will write it here. We find bending moment, right? Carefully focus. We find bending moment for the section AB, right? Right? That is affected, right? Or in other words, let's say, or in other words, right? In other words, bending moment due to the existing loads or forces at a distance of x, at a distance of x from the left end. Bending moment, actually it is the bending moment that is affected, right? Bending moment that is affected to the position, bending moment that is affected to a position which is at x distance from left. So that means you are going to find the bending moment due to the existing forces at here. Agree? Because of the distribution of force. So most of the time students, they do not know actually where, right, what is the exact point where the bending moment is acting, right? So that is the point where most of the students get confused, right? So actually the bending moment is acting at a distance x measured from the left end, right? That means the bending moment is acting at here because of the existing forces, right? So now let's write what is the bending moment. I will erase all those, right? Okay. So now erase this one also. So bending moment for the section AB. So now bending moment, I told you, when left side goes up only it is possible, but here left side will go down. So what is the force? Force will be force we know, force is 30 into x, right? So what is the moment at here? What is the moment at here? This is the point when it is measured x distance from here. So this is the point, right? So the center of gravity is right at mid, x divided by 2. That means from here to here also, see? That means from here to here also, here to here also the distance is x divided by 2, right? Because you are going to find the bending moment at this position, right? Okay, so we are going to find the bending moment at here. So now, what is that distance? Perpendicular distance, right? Distance from center of gravity. See, here the center of gravity is at here, right? Right? For this section, center of gravity is at here, right? So what is the distance from COG to the point where we are going to take moments? X divided by 2. But what is the sign? The sign is negative, right? Why? It is negative bending moment, right? So what is the equation? Equation will be minus 30 x squared divided by 2. That means minus 15 x squared. Okay, so that is how, let me check the answer. Yes, minus 15 x squared, right? So that is how we obtain the answer, right? So now at x equals 0, it says that bending moment equals 0. At x equals 1, it says that bending moment equals minus 15 kilonewton meters, right? Okay, so that is the point, right? So now we will consider for another. So now let me teach you how to consider the next section, right? So now consider the point C, right? So now point C is the position where this uniformly distributed load ends, right? It is where this 30 kilonewtons per meter uniformly distributed load chapter ends, right? So we will consider point C as the end point of the next section, right? So when I write, you will understand. So now consider the next section BC. Let me tell you why. The reason A to B is a section. This A to B is a section that we have already considered. Right? Let me write that now. 0 greater equal x lesser equal 1. This is a section that we have already considered. Right? So now the next section is a section which will be completely a new section. Right? Okay. So that means, so now this point C is actually at a distance of 2 meters from the left end A. So now our next section is we are going to cut the section little bit before C. Little bit before C. See, this is where I have cut the section. So what is this x? X is the distance from this starting position or this left end or the starting point A to a position that is little bit before C. Right? Not up to the C. Be very careful. Not up to the C. At a distance that is measured as x from the left end up to here. This is actually little before C, right? So now we are going to consider the section for the section, right? So let's call it section BC. But be very careful. Now here this section BC is actually greater equal 1, right? Lesser equal 2, right? I hope you got it, right? So now let's write for shear force. Now I told you, now see, we have a force that causes left side to go up. See this RB. So now this RB is actually positive, right? And we know what is RB. What is RB? RB is 73. We know what is RB, right? That's right. RB is 73. See, this reaction force actually causes the left side to go up. So positive 73, and what else? And we have this uniformly distributed load up to this point, but the resultant is pointed towards downward direction, right? So it will be minus 30 kilonewtons per meter multiplied by x, right? So now what is the general equation for the shear force? 73 minus 30x. Now this is the general equation for shear force for the section BC, right? Okay, it's very easy, right? 73 minus 30x. Is that correct? Yeah, 73 minus 30x, right? So now we have to put this lower end, the lower limit value and the upper limit value, right? So this is the way, this is the procedure, right? When x equals 1, it implies that shear force equals x equals 1 means 73 minus 30 into 1 is 30 equals 43 kilonewtons, right? Then when x equals 2, it implies shear force equals 73 minus 30 into 2 means 13 kilonewtons. Got it? Right? So that is also very, very important, right? So now all these critical values are very, very important, right? So now what is the next thing? Next thing will be for the same section we are going to write. Now we are going to write for bending moment, right? BM. I will erase this part, right? I will erase this part, right? Now I will erase this part. Now what is the bending moment? Now carefully you have to do simplifications because otherwise, because lots of variables are there, right? So now bending moment, right? So now be very careful. Now when we are going to consider the bending moment, I will again write this section to have a better understanding, right? So now we have cut the section at here, right? So what is the length of this section? That is x. Right? Length for this section is actually x, right? So now the entire, right, the ideal section ends at a distance of 2 meters, right? Keep that in mind. Now 2 meters is somewhere here. Now see, that is somewhere here, right? So we are going to cut little bit before x, like a little bit before the end, right? That is what we call as x, right? Now be very careful. Now we are going to find, again I am telling that we are going to find the moment that has resulted here. Moment at where? At here. Moment at here, because of the existing forces, right? That is what we are going to find as the bending moment. So now because of this reaction RB, you can very clearly see that the because of this reaction RB, it will exert a moment that causes the left side to go up, to go in the upward direction, right? Because of this reaction, the left side will move along the upward direction. That means positive bending moment, right? You got it. So now how to take the distance? Now see, the distance from this end to this section to this end of the section is x, right? Be careful, people. Be very careful. Now this is our section, right? The distance from this starting point to the end of the section is x, right? But this reaction force RB acts over there. So what is the distance? The perpendicular distance. What is the distance from this force to this end of the section, right? So that will be, now we know this reaction is at a distance 1 meters from this end, right? So what is this small distance? So that will be x minus 1, right? You got it? So RB times x minus 1, this perpendicular distance. So 73 times x minus 1, and it is positive, right? Now these are the now these are the areas where you have to pay a very great attention, because even a tiny error, right, definitely 0 marks. So be very careful. Huh? And the next thing is that the next thing is because of this uniformly distributed load. So now this load has continued for a distance of x. So what is the total load? 30 into x, right? And where the center point, what is the center of gravity of that distribution? It will be exactly at the mid position, right? Because it is symmetric, right? The symmetric position is, shall I sketch that again? Then you can understand properly, right? So the section ends at here, right? Section ends at here. So this is the distance, right? Here we have the load, right? Here we have the load, right? So what is the total force? T multiplied by x, it acts at the mid. So what is the perpendicular distance between the center of gravity of the uniformly distributed load and to the point where we are going to take the moment? So that will be x divided by 2, right? This gap. So that will be minus 30 into x, and x divided by 2. So you can cut that, then minus 15x squared. So 73 times x minus 1 minus 15x squared, right? Okay, and I hope you got it, right? So now let's simplify that. Then it will be okay, we'll better simplify that. Minus, so the final equation will be, right, carefully take up, minus 15 x squared positive 73x minus 73. Don't make any errors, right? So now that we will find it here, right? So now let's put the lower limit. When x equals 1, the bending moment will be, now x equals 1 squared is 1, so minus 15. 73 into 1 is 1, positive 73, and then minus 73, minus 73 cut, minus 15 kilonewton meter. Is it correct? Yeah. When x equals to, bending moment will be 2 squared. What is 2 squared? Be very careful about the calculation. Minus 15x squared. 2 squared is 4. 4 into 15 is 60, right? So minus 60. 73 into 2, 73 into 2, 146, right? And minus 73. So what is the answer? So 146 minus 73 will be positive 73, right? Positive 73 minus this 60. So 73 minus 60 is, what is that? That is 13 kilonewton meter, right? Yeah. Okay, right. So now again we have to continue with the sections, right? Okay. And we have to do the calculations for section CD, DE, EF, FG and GH, right? Okay. Now it doesn't matter. No, I will consider, okay, I will consider a different section, right? And not only different, I will consider the most difficult section for you to evaluate, right? Okay, so now we know that we have several sections, right? We have already evaluated AB and BC, and we have to evaluate section CD, DE, EF, FG and GH. Now I will consider the most, the hardest section, GH, right? So now actually what we are doing during this evaluation, now we are going to cut this section. See, I am going to cut from here, right? That means I am going to cut a little bit before this end H, right? So this is my section, so I am going to cut from here, right? So now the distance from this left end to here is X, right? So now I am going to consider this section. I am going to define this section GH, right? Where it is something like 6 greater equals X lesser equals 8, right? So that is how I am going to define the section GH, right? Okay. Now what is the very first thing that I have to do now? I have to consider the shear force. Shear force for the section GH. So now what is the first shear force? That means we have to consider this entire distribution, but because of this load, the left side is going down. So it is no doubt minus 30 into 2, right? Then because of this reaction, that is RB, that equals 73. This side will go up, right? So positive 73, right? Then you don't have to worry about the applied moment. Then because of this 20 kilonewton load, the left side goes down. So negative shear, so negative 20. Then again we have this one. See, what is this? Positive 40 kilonewton at here. So because of this load, the left side will move upward. So positive 40. Now we have to consider this triangular load. See this guy. I will give a name. Let's say this triangle PQR. Triangle PQR. Right? Right? So that is only under this section, right? So not the largest one, not the larger triangle, this triangle. I will just hatch this triangle, right? So now in that triangle, we have to do some simplification, something related with triangles, right? Just consider this smaller triangle under the section, which is PQR, right? Some little calculation is there. Now this is the smaller triangle, right? And consider this one, the large original one. What is that? That is the larger one, right? We know this length. What is this length? 100. But here, what is this length? We don't know that, so let's call it 5. We know this length, base, that is 3. Do we know this one? Yes, this one you can calculate because 1 meter, 2, 3, 4, 5. So what is this length then? The total length from here to here is X. Then up to here we have 1, 2, 3, 4, 5. So then this small distance will be X minus 5. Right? So what is this length then? X minus 5. So now we are going to use some small theorem, right? This is how we define that. Okay. 100 divided by 5, 100 divided by 5 equals 3 divided by X minus 5. So this unknown 5 equals, what is 5? 100 times X minus 5 divided by 3, right? Because we need to find that in order to evaluate this load. So now we know, I will erase that. So now we know that because of this triangular load, the resultant is acting along the downward direction. So because of that resultant load, the left side will go down, right? So then it will be minus, I will write it at a side. 5 equals 100 into X minus 5 divided by 3. Okay. Now, so that will be minus half into base. What is the base? Base is X minus 5. Half into base into height. What is height? That is 100 into X minus 5 divided by 3. So now let's simplify. Let's simplify this. 60 minus 60, 73 means 13, minus 20 plus 40 means positive 20, half, this is 50, then it will be minus what? Minus 50 times x minus 5 square divided by 3. So 33 minus 50 times x minus 5 squared by 3. Right? So now that is the equation for the shear force. Right? Now right. So now we need to evaluate the shear force at x equals 6. Also we have to evaluate the shear force at x equals 8. So the shear force at x equals 6 will be, if you put 6 here, 6 minus 5 is 1 square. So 33 minus 50 divided by 3. What is the answer for that? 3 into 33 is 99 minus 50 divided by 3. What is that? 49 divided by 3 49 divided by 3 kilonewton meter. Not kilonewton meter, kilonewtons. 49 divided by 3 kilonewtons, right? Because this is the shear force factor. At x equals 6, the shear force is 49 divided by 3. Let me check it. At x equals 8, it is, what is that? 33 minus 50 times 8 minus 5 is 3, 3 squared is 9. See, 8 minus 5 is 3, 3 squared is 9. 3 times 3, 3 times 1 and 3 times 3. Then it will be 33 minus 150. The answer, the shear force at x equals 8 will be minus 117 kilonewton. Shear force at x equals 8 is minus 117 kilonewtons, right? Okay, so now let's move on to the bending moment diagram, right? Right. Okay. Now, bending moment for the section GH, right? Bending moment for the section GH, right? Now it is very easy. Now just consider the directions because of this load, this distributed load. Left side is going down, so minus 30 into 2. Now you have to consider the perpendicular length. The length from here to here, that means the length from this extreme left side to the center of gravity of this distribution. So now where is the center of gravity of this distribution? It is right at the mid. This is 2 meters, so the center of gravity is right at here. So the distance to the center of gravity from the left end is 1. So the distance from here to here will be x minus 1, right? Do you understand? Center of gravity is portion at here, right? So the distance from this left end to here is 1. But we have to consider the distance from the center of gravity of this distribution and up to this end, because now we are going to get the moment at this section. That means moment at a distance x, right? We are going to take moments at a distance x, right? So minus 30 into 2 times x minus 1. Okay, then this one 73 going upwards, so 73 times x minus 1. Then here we have this applied load. Definitely the left side is going up, so positive 60. Then because of this, 1, 2, 3, 4 is going down, minus 20 times x minus 4, right? Then this one, 1, 2, 3, 4, 5, 6, right? Yeah, so because of this upward force, the left side is going up, so positive 40 times x minus 6. Now wait, so now just consider this triangular load. Now where is the center of gravity of that triangular load? It is somewhere at here, right? That means 2/3 of this base. Remember, what is this base? X minus 5 is this base, right? So now what is the center of gravity of that resultant? 2/3 of this base starting from here. That means from here, 2/3 of the total. So it will act over here. The position of the center of gravity is 2/3 of the base starting from here. So then you have to consider the perpendicular distance. What is the perpendicular distance? This small length. So that small length will be, what is that small length? That will be 1/3 of the base, right? 1/3 of the base. What is the base? X minus 5. So then anyhow the effect of the bending moment because of this triangular load, that is negative half. What is the base? X minus 5 is the base. What is the height? Wait. What is the height? Height will be 100 times x minus 5 divided by 3. And what is the perpendicular length? That will be x minus 5 divided by 3. So now let's simplify. 60 into x minus 1 minus, then if you simplify these two, it will be 13 times x minus 1. Here positive 60, okay, no problem. Minus 20 times x minus 4. Positive 40 times x minus 6. If you simplify this one, 250. Then minus 50 divided by 9. 1, 2, 3 x minus 5 cube. Minus 50 divided by 9 x minus 5 cube, right? Now I will use this one. Right, okay, so now let's find what is the bending moment at x equals 6. Then put x equals 6 here. 13 into 5 plus 60. X equals 6 means minus 20 into 2. This will cancel. Minus 50 divided by 9 times x equals 6 means this side is 1. 13 into 5 how much? 65 plus 60 minus 40 minus 50 divided by 9. 60 minus 40 is 20. 85 minus 50 divided by 9. So LCM 9 into 5 45. Balance is 4. 8 into 9 72. 72 for 76 minus 50. 765 minus 50 divided by 9 will be 715 divided by 9. Bending moment at x equals 6, right? Now let's consider bending moment at x equals 8. So what will be the bending moment at x equals 8? What is the general equation? General equation is 13 times x minus 1. So 13 times x minus 1 means 13 times x minus 1 means 8 minus 13 times 7. Plus 60 will be there. Minus 20 times x minus 4. X minus 4 means now x is 8. 8 minus 4 is 4. Plus 40 times x minus 6. Plus 40 times x minus 6 means 8 minus 6 is 2. Then the next one, my 50 divided by 9. Right. Then minus 50 divided by 9 times x minus 5 cube means 8 minus 5 is 3 cube. 3 cube. 3 cube means what is the answer? 3, right? So 13 into 7, what is 13 into 7? 70, 20, 91. 91 here. Then 60 minus 80 plus 80. Cancel. Minus 150. What is the answer? 151 minus 150. The answer is 1 kilonewton meter. Actually here there is a problem, right? And let me tell you that. So actually the reaction force RB is not exactly 73 because there is a decimal error. Because the actual value for the reaction at RB is, it is actually 72.857. 72.857, right? So that is the actual scenario. It is not actually 73, right? The answer for RB we are not exactly obtaining a whole number, right? So we have just rounded that. See, we have rounded it up to how many decimals? Right? see 0.043, right? So we have given additional 0.043, no, not 0.043, 0.143. Did you see that? Right, so that means we have given additional 0.143 decimals in order to make it to 73. So that means definitely there is a decimal error, right? Okay, right? But actually, but theoretically, if you are going to consider the bending moment at the last point, right? Theoretically, if you are going to consider the bending moment at the last point, this value actually must be 0 kilonewton meters, right? So when you do some future problems, you can understand that, right? So at the last section, if you put the last section, if you are going to put the higher limit, this is the last section. So if you put the highest limit x equals 8, actually theoretically you must obtain it as 0 kilonewton meter, right? So because of that decimal error, we are getting it as 1, right? Okay, right? So now the next section is section CD, right? So now when you are going to consider the section CD, the section CD we define in such a way that 1, 2 greater x lesser 3, right? But sometimes we say 2 greater equal x lesser equals 3, right? But we can even write like that also, right? But actually this equation is valid when we write it like this, right? Not actually when x equals 2 and not actually when x equals 3, right? Because sometimes we write like this also, right? Like when you are going to define the section, right? I will tell you that clearly, because sometimes when we are going to define the section, we write it as 2 greater equals x lesser equals 3 also, right? But that relationship is not actually valid when it is exactly at the lower limit and also when it is exactly at the high limit, right? So better will write like this, right? Section CD, right? 2 greater x lesser 3. So now let's write shear force. Left side going up forces, okay, minus 30. It is minus 30 into 2, right? Because of this minus 30 into 2, the left side will go down, right? Then we have the reaction RB, left side going up, then plus 73. Minus 60 plus 73 is what? 13 kilonewtons, right? Then bending moment, we are going to take moment at a point x distance away from here, right? That means like when we are going to consider for the section CD, we are going to cut little bit before D, right? That means this applied moment is not actually applied, right? That's the scenario that you have to understand, right? We are going to cut little bit before D, right? So then let's write for the bending moment, right? Equals minus 30 into 2. The center of gravity to the distributed load is 1 meters from here. Then the perpendicular distance will be x minus 1, right? And then positive reaction RB is 73 times x minus 1, right? Because distance from here to here is x and here to here is 1, so x minus 1, right? So then 73 times x minus 1 minus 60 times x minus 1 means 13 times x minus 1, right? 13 times x minus 1, right? So then according to here, when now put the lower limit, when x equals 2, right? When x equals 2, it says that bending moment is 13 kilonewton meters, right? When x equals 3, it implies that bending moment is 26 kilonewton meters, right? Okay, 13, 26 and 30, right? So now let's consider for the section D, right? Now D means this section D, that means we are going to cut little bit before D, because now this is D, where this applied moment is there, this is D, this is E, right? This is E, right? So we are going to cut little bit before E, right? That means the better way of defining the section is 1, 2, 3 greater x lesser 4, right? So that is the better way to define the section, right? So now what are the forces that will apply? Shear force. Now you know how to apply, right? So minus 60 plus 73 Is that all? Yeah, because this 20 kilonewton is not yet applied, right? So then shear force will be 30 kilonewton, right? Shear force is 13 kilonewton, right? Let's apply for bending moment. When applying for bending moment, right, you know that it is minus 30 into 2 times x minus 1, right? Because why x minus 1? Because you have to consider the distance from center of gravity to this point where we are going to take moment. So this distance is here to here is 1, right? Right, here to here is 1, right? So this distance is x minus 1, right? So minus 16 into x minus 1, positive 73 into x minus 1, and plus this positive applied moment. What? Positive applied moment, that is 60. So the bending moment, actually the bending moment equation will be what? 13 times x minus 1 plus 60, right? 13 times x minus 1 plus 60, right? So then when x equals 3, what is the bending moment? 3 to 26, 86 kilonewton meters. When x equals 4, the bending moment will be 39 plus 60, 99 kilonewton meters. So now let's consider the section EF, right? EF means here, right? Yeah, right. So now we are going to cut little bit before F, right? Little bit before F. That means EF section we will define in 1, 2, 3, 4. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. That means we are going to define the section EF in such a way that 4 greater x lesser 5, right? 4 greater x lesser 5, right? So now let's write the shear force. We know how to write the shear force. Now it is like familiar to us, right? Minus 30 into 2 plus 73. Then this minus 20 kilonewton, right? Because going down, right? Because now when x is greater than 4, that means this 20 kilonewton is included, right? Because now why the region is now x is greater than 4, right? So what is the shear force? 13 minus 20 minus 7 kilonewtons, right? So minus 7 kilonewtons is the shear force, right? Throughout the section, right? Now this is not actually valid when x equals 4 and when x equals 5. This is not valid when x equals 4 or when x equals 5, right? So that is the thing that you have to keep in mind, right? Right. So now let's write bending moment, right? The general equation of the bending moment, right? Minus 30 into 2 times x minus 1 plus 73 into x minus 1 plus 60, right? Then 1, 2, 3, 4, right? Then negative 20 into x minus 4, right? 1, 2, 3, 4, yeah. Then what else? That's it, right? So general equation for the bending moment will be 13 times x minus 1 plus 60 minus 20 times x minus 4, right? Now put x equals 4. X equals 4 means 13 into 3 plus 60 minus 20. X equals 4, right? Then 4 minus 4 is 0. This will cancel, right? So 13 into 3, how much? 39 plus 60, 99. So 99 kilonewton meters, right? At x equals 4, right? At x equals 5, 13 into 4 plus 60 minus 20 into 5 minus 4 is minus 20, right? 13 into 4 is how much? 52 plus 60 minus 20, right? So 112 minus 20. 112 minus 20 is how much? So that will be 92 kilonewton meters. The last section, right? What is the last section? Last section is last section is FG, right? So now the last section is FG. That means that we are going to cut a little bit before G. So we are going to cut from here. Now what is this distance from here to here? Distance, that is x. Okay. Right. Okay. So now you know the story, right? Section FG. FG we are going to define in such a way 1, 2, 3, 4, 5. And this is 6, right? 5 greater x less than 6, right? Now previously also that I have told you, right? Because sometimes we can write this like 5 greater equals x lesser equals 6, right? But as a region we can write, but I think it will not be nice to define the section like that, right? Because now the general equation, right? Actually now that general, because now later we are separately going to find, right? That is every time I am telling you this, right? Because later we are separately going to find what is the exact shear force at x equals 5, right? What is the exact shear force at x equals 6, right? Because we are separately going to find that, right? So that means when considering the section, right, it would be much better if you write like that, right? Because that general equation is not valid when it actually reaches the lower limit and when it actually reaches the higher limit, right? So now let's write the shear force. Now I think you can remember, right? Minus 30 into 2 plus 73, applied moment law, then minus 20. Then now tell me one thing, this 40 kilonewton is considered or not? Actually not considered, right? But this section up, now here you can see this uniformly varying load up to this x distance, right? This little part is coming, right? That is the most important part here, right? But here when you are going to consider this uniformly varying load up to here, that comes, right? Because like that uniformly varying load up to this cut, that comes, right? Now you know how to define that, right? Now consider the larger triangle. This length is 100, right? And then you know that this total length is 3, right? And for the smaller section, let's say you don't know the height. Let's say that you don't know the height for the smaller section, right? You don't know the height for the smaller section, right? So let's call it 5. And you know the base for the smaller section. So what would be the base for the smaller section? 1, 2, 3, 4, 5. So that would be x minus 5, right? Again, shall we check 1, 2, 3, 4, 5, right? So this, the width of this, the base length of the smaller section is x minus 5, right? Right. Now not up to here, it's up to here. So let me sketch that again, right? The base length for the smaller section, x minus 5, right? Okay, so now let's see how to find the value of this 5, right? Okay, so let's see how to find that. Now you already know how to find that, right? So that is actually the way of finding is, there's some little ratio theorem we are going to use, right? 100 divided by 5, 100 divided by 5 equals 3 divided by x minus 5. So like 5 equals 100 into x minus 5 divided by 3, right? Okay, so then that portion is coming, right? Okay, but here it is going down, so negative, you have to get the area. Previously also we have done something like that. So minus half into base x minus 5 into height. Now what is the height? 100 into x minus 5 divided by 3, right? So now that is the shear force equation, right? So 50 divided by 3, x minus 5 squared, right? So shear force general equation will be here 13 to 260, 13 minus 60 plus 73 is 13, 13 minus 20 minus 7, right? Minus 7 minus x minus 5 squared into 50 divided by 3. Am I correct? So let us write it again, minus 7 minus 50 divided by 3 x minus 5 whole thing squared, right? So that is the general equation for the shear force, right? So now put x equals 5. When x equals 5, you don't have to worry about this part, right? So only minus 7 will be there. So minus 7 kilonewtons, right? The shear force. Okay. Right. Now I will erase this part, right? Otherwise I don't have space. Now when I write x equals 6, when I write x equals 6 there to the general equation, so minus 7 will be there, minus 50 divided by 3, 6 minus 5 is 1, right? So minus 7 minus 50 divided by 3, minus 7 minus 50 divided by 3, minus 21, minus 50 divided by 3, minus 71 divided by 3 kilonewton meters, minus 71 divided by 3, right? So that is for the shear force, right? Okay, this length for the phi is very important, right? Otherwise it will be a problem, right? Phi length, I need the length of phi 100 x minus 5 divided by 3, right? Now shear force values I have evaluated, right? Now for the bending moment, okay? Now for the bending moment, right? Bending moment, general equation, right? Minus 30 into 2 into x minus 1 plus 73 into x minus 1 positive 60 1 2 3 4 minus 20 into x minus 4, and then okay, now what is the center of gravity from here to here? Now we know the base length. Now what is the base length? Is x minus 5, right? So the center of gravity will be 2/3 of the base length. That means center of gravity will be at here. So the length from here to here will be 1/3 of the base length, right? So then minus the area half into base x minus 5 into height 100 into x minus 5 divided by 3. Then 1/3 of the base length. 1/3 of the base length means base length is x minus 5, then 1/3 of that. Okay, done. 2 cut 50. So then it will be 50 divided by 9 x minus 5 cube, right? I think so that is the equation, right? So I will write that answer here. The bending moment, general equation equals this 13 into x minus 1 plus 60 minus 20 into x minus 4 minus 50 divided by 9 x minus 5 to the power 3, right? So now how about the sections? FG sections, when x equals 5, you have to find the bending moment. Then again you have to find the bending moment when x equals 6. When x equals 5, 13 times 5 minus 1, bending moment equals 13 into 4 plus 60. The 5 means 5 minus 5 is minus 20, right? Minus 50 divided by 9. 5 means this part will cancel because 5 minus 5, right? So this part will not come. So bending moment will be like 13 into 4, 52 plus 60 minus 20. The answer will be 92 kilonewton meters, right? 92 kilonewton meters, right? When x equals 6, bending moment will be 13 into 5 plus 60 minus 20. No, not minus 20. Minus 20 into 6 minus 40, right? Minus 40 minus 50 divided by 9, right? Because like 6 minus 5 is 1, right? So then 13 into 5 is 65 plus 60 minus 40 minus 50 divided by 9. How to simplify? 60 minus 40 is like 20, so 85. 85 minus 50 divided by 9, right? 85 minus 50 divided by 9. So how to simplify that? Okay, I will go here. Bending moment equals 85 minus 50 divided by 9. SEM is 9, right? 9 into 5 is 45. 4 balance. 9 into 8 is 72, right? Then 72 plus 4, 76 minus 50. Answer will be 715 divided by 9 kilonewton meters. 715 divided by 9 kilonewton meters, right? Okay. So now we have evaluated, right? So now carefully see, right? So now we have evaluated for all the sections, right? And then again, like I have to tell you that when considering the section, better use the section greater than a lower limit and lesser than upper limit, right? It is better if you not include the equal symbol, right? Because now the general equation is not ready. Again and again I am telling, right? So now we have evaluated the general equation. Now be very careful. This is something that I have noted. Now we have the final step, right? Now what we will have is to do the final step, right? Very final step, right? So now that is the special feature in bending moment, right? So we have to do the sectioning, right? Then sectional shear force, sectional bending moment, then upper limit value, lower limit value for shear force and bending moment separately. Then the final step is to sketch. Okay, so in the last part we will see how to sketch the bending moment diagram and also how to decide the increasing type of curve and decreasing type of curve, right? That is also very important, right? So now I'm going to discuss the sketching of the shear force diagram, right? Okay, so now I will explain how to sketch the shear force diagram, right? So now first of all, now here you can see that I have sketched the loading diagram, right? So now carefully you have to sketch the loading diagram, right? Because now we are going to sketch the shear force diagram and bending moment diagram with respect to the respected sections that we have considered with respect to the load diagram, right? So because now this is the load diagram, just see carefully. This is the load diagram of the problem that is given to us. So with respect to each and every section that we have done calculations, we are going to sketch the shear force diagram and the bending moment diagram. Now first let's consider the shear force diagram, right? Okay, so now I have obtained the summarized values, right? Now summarized value for each and every section and the shear force values, right? And here you have to consider the general equation for the shear force and as well as the respected lower limit value for the shear force and the higher limit value for the shear force. Now first we will only consider the shear force. Now let's consider the very first section that we have considered. Now what is the very first section that we considered? We considered section AB, right? So when you have considered the section AB, right, when you, because now you already defined the section, right? You already defined the section in such a way that for the section AB that 0 greater x lesser 1. So like that you define the section, then you put the lower limit as 0, you obtain the value, then you put the higher limit as 1, then you obtain the value, right? Now the very first thing under the section AB, right, under the section AB, just mark the value. Under the section AB, mark the value of the lower limit 0, value of the higher limit minus 30. Now this is minus 30. See, this one is minus 30, right? So now how you are going to connect that? So that is the point, right? So that the way that you are going to connect, right? That means like in order to connect, you need some sort of a relationship, right? Whether a first degree curve, second degree curve, or a straight line. Okay, so like that. So the way you are going to connect is the problem now. Now just look at the general equation. Now here you can see, if you focus the general equation, it is the general equation is minus 30x. Okay, so now you know the standard equation for a straight line, so that is y equals mx plus c. So as this is minus 30x, that means you can see negative gradient. So negative gradient means, right, so you know if the gradient is negative, the angle is an obtuse angle, right? If the positive gradient, the angle is if the positive gradient, the angle is an acute angle. See this angle, right? If positive gradient, acute angle. So if negative gradient means the angle must be an obtuse angle, right? Obtuse angle. So see, it's a no. Now when you're going to consider x-axis, the angle that the line makes with the x-axis is an obtuse angle. See, so you are going to connect by a line like that, right? How did you connect? How you thought to connect like that? That is from the general equation, right? So now this section is okay. You are going to connect like that. So then consider for the section, next section. Now consider for the section BC. Now if you are going to consider for the section BC,
What is the lower limit value is 43. Higher limit value is 13. Just go back to the calculations, right? Lower limit value is 43, higher limit value is 13. So first mark the lower limit value. So what is the lower limit value? Now we are going to consider for the section BC, right? So now when you are going to consider for the section BC, right, you are getting one answer at the point B from the previous step, right? If you are going to consider for the section BC, you are getting one answer for that point from the previous section and another answer from the next section, right? It doesn't matter. So what is the first value that you are getting at the lower value, like what is the value according to the lower limit? 43. So just mark 43 over there. What is the next one? Higher limit value 13. So just mark 13 from here. So this is 43 and this is 13, right? So then connect that. So how you are going to connect? You are going to connect from a line. Now see this line that you have sketched. This line makes an obtuse angle with the x-axis. Why? Because the gradient is negative gradient, right? Okay. So now as for the section CD, 13, it is a fixed line, right? So you don't know. If you again go through the sectional calculations, there is no need of a general equation for that because it is a fixed value. See, for the section CD, the value is continued, 13 to 13. Then for DE also it is same, 13 to 13. Again go back, it is not a magical thing. Again go back to the calculations, DE 13 to 13, so it is fixed. See, DE 13, 13 is fixed. So now if you are going to consider for the section EF, right? So now you can see if you're going to consider for the section EF, the lower limit value is -7, high limit value is -7. See, EF -7, and that means at E, at the lower limit it is -7, then higher limit it is -7, but they are also according to the section EF, you don't need any general equation, it's a fixed line. See, so that is how you have sketched. See, now this is a straight line, right? Okay, now for the section FG, right? Now focus the section FG. Now for the section FG, now here you can see it's a second degree curve, right? What sort of a curve? Second degree curve. So this is the value of the shear force at the lower limit, value of the shear force at the high limit. Now first mark those two values, value of the shear force at the lower limit and value of the shear force at the higher limit. Okay, so now for see, this is -7, right? The value according to the lower limit, -7. The value according to the high limit is -71/3, that is over here. So now you have to connect that. See, I told you when connecting there are two types of curves, increase in curves and decrease in curves, right? So now shall I sketch that again? So when connecting, I told you there are two types, increase in curve type and decrease in curve types, right? Increase, this is the increase in type and this is the decrease in type. So now here when connecting this one, like -7 to -71/3, you have sketched it as an increasing line, right? The line of this type, right? Why? Because see, now this section, the shear force for this section actually based upon this loading. You can see this uniformly varying load. Just focus the uniformly varying load, right? So here you can see the load intensity is increasing little by little, it is increasing, so it's an increasing curve. Done. Okay, right? So then the next section, it is a GH, right? So now for GH, what is the lower limit shear force? 49/3. So 49/3 is here, right? Now I told you for the GH also there is another value that is coming as the higher limit for the point G and lower limit for the point G, right? Okay, so now what is the lower limit value for the section GH? It is 49/3. Now mark 49/3 over here, right? 49/3 over here. Then the higher limit value is -117. So -170. See, -117 is over here. This is 49/3, this is -117, right? So you have to connect these 2 points. Now when considering that connection, you must know what is the pattern, what is the line. So for that you need the general equation, right? So now see, this is a second degree curve, right? And the other thing is, see, here also the intensity is increasing. See, intensity increasing, so the line of connection must be an increasing curve. See, increasing, that means this type, right? And now when connecting these 2 points by an increase in type curve, you must know definitely there must be an intersection where this curve intersects the x-axis, right? So that's all about the shear force. Okay, right? So now let's consider the sketching of the bending moment diagram, right? So now for the bending moment also, right, we are going to sketch the bending moment diagram with respect to the sections that we have considered in the calculations, right? So now first thing is consider the section AB, right? For the section AB, the general equation for the bending moment is -15x squared, which is a second degree curve. The bending moment at the lower limit is 0, higher limit is minus 15. So first of all mark that, see, right? 0 and minus 15. So now we have to connect that. So how to connect that? Now it is a second degree curve, right? So is it an increasing curve or a decreasing curve? Just look at the type or look at the order of this function, right? So in order to connect these two limits, right, starting from 0 to minus 15, the only possible way is sketching it through an increasing type of a curve, right? Increasing curve type, right? Okay, right. And then for the next one, for the next bending moment, like for the next section BZ, now we are going to sketch for section BZ, right? So now for section BZ, the lower limit bending moment is 13, higher limit is 26. Now first mark that, right? 13 lower limit, right? And upper limit it is 26, right? Over here, right? This must be the same curve, right? Now just look at the order. So it is a second degree curve, right? So it must be a second degree curve, okay? And so that is sketched, see, second degree curve, minus 15 x squared plus 73 x minus 73. So we have to connect this minus 15 to this 13. So this is the possible curve, right? Increasing curve, right? Okay, but be very careful. It is this increasing type of curve is only up to here, right? This increasing curve is only up to here. See, one curve to connect these two, then to connect these two, right? So then the next section CD. Now see, the lower limit value is 13, high limit value is 26. Now see, 13 times x minus 1. So this is an equation of a straight line. Now that is what I'm telling you. Every time you have to consider the general equation, right, in order to determine the curve, right? So this is 13 times x minus 1. So if you expand that, it is 13x minus 13. So what is the type of the like what is that line? Actually it is a line, right? It is the equation. It is the standard equation of a line. And what can you say about the gradient? See, it is a positive gradient. Just look at 13x, a positive gradient. See, so this line makes an acute angle with the x-axis, right? So what is the lower limit is 13, then upper limit is 26, right? Okay, lower limit is 13, upper limit is 26. So you have connected it by a straight line. See, straight line. Okay, so then the section DE, then for the section DE, see, again it's a straight line, right? Again it's a straight line, right, with a positive intersection, right? See, 13 times x minus 13 plus 60, right? Positive intersection, right? And positive gradient also, 86, 89, 86, 89. See, lower limit bending moment is 86, then higher limit is 86, 99. See, this is 86, this is 99. So you have to connect it by a straight line, right? Okay, the next one EF. Next one is for the section EF. So what is for the section EF, what is the lower limit value? 99, right? For the section EF, the lower limit value is 99, then higher limit value is 92, and we have to connect it through a straight line and see why it is a straight line. So just focus here. So it is 13 times x minus 1 plus 60 minus 20 times x minus. So just simplify this and get the equation, right? So if you simplify this one, so it will be, see, 13x minus 13 plus 60 minus 20x plus 80, right? So if you simplify that, 13 minus 20 minus 7x, right? So then this it will be 47. 47, 80 means 127, right? Shall we check it again? 13x minus 13 plus 60 minus 20x minus positive 80, right? So we have 80 here, 140 here. 140 minus 13 means 127, positive 127. So 13, I see, minus 7x plus 127 means positive interception, but it's a negative gradient. See, it's a negative gradient. See, section EF, negative gradient means it is making an obtuse angle with the x-axis. See, making an obtuse angle with the x-axis. Because why? The reason it is a negative gradient, right? Because it is minus 7x. Focus that, okay? So this section is okay. Then go for this section FG, right? So for the section FG, this is the lower limit bending moment is 92. Lower limit bending moment is 92. Then see, lower limit bending moment for the section FG is, see, it is 92, right? Then the higher limit bending moment is 715 divided by 9. So this value is 92, then this value is 715 divided by 9. So then you have to connect these two, right? So then what sort of a, like, what is the curve type? See, is this a first order, second order? No, see, it's a third order. See, because the reason you have this x minus 5 to the power cube, right? So you have x minus 5 to the power cube, but again now look at that intensity. So intensity increasing, right? So from here to here, so it's an increasing type of a curve. See, increase in type. So bending moment is also increasing type, right? Increasing, right? From F to G. See, the load intensity is increasing. Then the last section GH, right? Section GH. So focus GS. So when considering the section GH, now this is the lower limit value, 750 divided by 9. See, this is the lower limit bending moment for the section GH. See, this one 715 divided by 9. This is the lower limit bending moment. Now higher limit bending moment, now like when considering the calculations, it is 1, but theoretically, like, it must be 0, right? Because 1 is also, like, I'm not going to say 1 equals 0, but this is because of the decimal error, right? Because I told you the reaction that we have considered 73 kilonewton is not the exact one. I have explained that in the previous part, right? So it doesn't matter, you can even keep as 1, but the better way is keep it as 0, right? So it is 0, right? Because the bending moment at this point, that must be 0. So the lower limit value is 715 divided by 9 here, and then here 0 kilonewton meter bending moment. So you have to connect this. The connection must definitely be this connection must be made by an increase in type curve, because the load intensity is increasing, right? And again, also look at the curve. Every time you have to get this, like, the curve type, 13 times x minus 1 plus 60. See, because of this part, it has become, see, because of this part, right? Yeah, so it has become a third degree curve, right? X minus 5 cube. So this is how you are going to connect it. Increase in type of a curve. So this is how you are going to sketch the shear force and bending moment diagram, right?